In our last lesson, we studied the physics of fluids at rest. The field in fluid mechanics referred to as hydrostatics. We discussed how fluid pressure gets exerted equally in all directions at a given point in a fluid. We discussed how the force on a surface due to fluid pressure must act perpendicular to the surface. We discussed how the pressure in a fluid increases linearly with fluid depth. We discussed how changes in pressure to a confined fluid get transmitted throughout the fluid, what we call Pascal's principle. And finally, we discussed this net upward force acting on objects immersed in fluids at rest called a buoyant force. And we saw how to calculate buoyant forces acting on objects using Archimedes' principle. But now we want to ask the question, what happens when objects are immersed in fluids that are in motion, when fluids are moving? This is the branch of fluid mechanics we call hydrodynamics. As you'll see in this lesson, some rather interesting and unexpected physics comes into play when fluids are in motion. Let's take a look.
Have you ever seen the love between a ping pong ball and an airstream? We're going to use this air source to demonstrate the attraction that a ping pong ball will have for a moving stream of air. This air source will blow out air. I'm going to place the ping pong ball in the air source, and you'll notice that even as that airstream moves to the right and to the left, that ping pong ball will remain attracted or fixed in that stream of air. We can explain this using Bernoulli's principle, which we'll talk about shortly. But first, let's demonstrate this.
So in thinking about the demonstration that you just saw, when the air source was in a vertical position, perhaps it wouldn't surprise you that the ping pong ball remained afloat. You might reason that the upward force of air was opposing the downward force of gravity. But what about when the air source was held at an angle? How can you explain the fact that the ball remained there at rest rather than accelerate? So let's take a look at a free body diagram. In this case, you can see that clearly there's a downward force of gravity acting on a ball, and there's the force of the airstream acting on it at an angle. But is that ping pong ball disobeying the great master himself, Isaac Newton? Clearly, there must be another force that we're not accounting for if the ping pong ball is to remain suspended at rest in a state of mechanical equilibrium. We'd better figure out what this unknown force is, or you can kiss goodbye everything you learned about Newton's second law. So we'll begin our investigation into this unknown force by taking a look at two different types of fluid flow. The first type of fluid flow is what we call streamline or laminar flow. The second type is what we call turbulent flow. Let's take a look at the characteristics of each of these types of fluid flow so that we can distinguish between them. Starting with streamline or laminar flow, the illustration I'm showing you over here on the right shows you various streamlines. And a streamline, I'll trace out one of these streamlines. A streamline is simply the path that a layer, or let's say small sample of fluid, will take okay, in its motion. You can see here that adjacent streamlines, that is adjacent layers of fluid, slide smoothly past each other. These streamlines never cross, and that's characteristic of laminar flow. You'll never see streamlines crossing each other because, okay, different layers or pieces of fluid slide smoothly past one another. You can also say that for streamline or laminar flow, if we look at a particular point in the fluid, okay, like where my laser pointer is right now, we can say that the fluid speed and direction or fluid velocity at that point remains constant in time. Let's contrast this with turbulent flow. It turns out, okay, that above some critical speed, okay, the fluid flow will become turbulent. And you can see here what happens in this pipe, okay, that the flow starts out in a streamline or laminar fashion where these streamlines are not crossing each other. But due to the constriction here, which as we'll see will cause the fluid speed to increase, okay, in this region over here, these layers of fluid no longer slide smoothly past one another. Okay, you get eddies or these little whirlpools, okay, to form. I'm going to show you in the simulation here, okay, you can see that for streamline or laminar flow here, this is a nice simulation because these different colors represent the streamlines of your moving fluid, and you can see that the layers of fluid don't actually cross each other, okay, as the fluid moves from left to right. Okay, as opposed to in the case of turbulent flow here, okay, you can see here that, okay, the fluid layers or streamlines are crossing each other. Okay, they're not sliding smoothly past each other. I thought this was going to be a give us changes in time, but I guess I was wrong on that. Now that we've talked about the difference between streamline or laminar flow and turbulent flow, we're now in a position to define what we mean by an ideal fluid. Because for the rest of this unit, we're going to be talking exclusively about the physics of ideal fluids. So first of all, we can say that when we talk about an ideal fluid, the fluid flow is laminar or streamline. Same thing. That is not to say that we can't talk about the physics of turbulent flow, okay, but that's not what we're going to be talking about in this unit. Okay, turbulent flow is far more complicated. It's a far more complicated topic involving nonlinear, okay, as opposed to linear dynamics. And we may discuss it briefly when we introduce the topic of resonance later in this course. And okay, we'll see, for example, if we try to explain the infamous Tacoma-Narrows bridge collapse, okay, a theory of vortex shedding, which involves hydrodynamics for nonlinear fluid flow, okay, for turbulent flow. This is a theory to explain it. But for now, we're going to stick with simpler systems where we can consider the fluid flow to be, okay, laminar. For the ideal fluid, we also assume that the fluid is non-viscous, in which case there's no frictional forces between adjacent layers of the fluid. So we can assume that the fluid layers will slide very smoothly past each other. So smoothly, in fact, that there is no internal frictional forces between adjacent layers. We can also assume that for an ideal fluid, the fluid itself is incompressible, which means that the density of the fluid remains constant. Obviously, this is the case for liquids. Liquids, we say, are fairly incompressible, but it is not the case for gases. So when we want to apply the physics of ideal fluids to gases, okay, we can do so as long as we realize that our answers are only approximations, okay, since the physics starts to break down when the density of the fluid changes in time. And we see that gases, their density is very subject to change, okay, with changing pressure conditions. And finally, we would say that fluid flow is irrotational, which means that if you consider a very small element of fluid as it moves, it has no angular momentum about any point, okay, in which case no eddy currents can form. So when you consider streamlines, okay, streamlines may curve, okay, suggesting the fluid moves in a curved path, okay, but for streamline flow, there is no 360-degree rotation, okay, of any streamline, okay, suggesting that there is no element of fluid, okay, that makes a full rotation as it moves in space. So if we're going to describe moving fluids, that is fluids in motion, we need to discuss the concept of flow rate. The flow rate measures how much fluid flows as well as how fast it flows. When it comes to how much fluid flows in a pipe, canal, river, gorge, or whatever, okay, we can measure the amount of fluid that flows by measuring either the mass of fluid or the volume of fluid that flows. So, we can say then that we have two ways to calculate flow rate. One in terms of mass, one in terms of volume. So let's start by considering a fluid that is moving through a pipe of varying cross-sectional area. So you can see here on the left, okay, when the fluid is at this point in the pipe, okay, it's moving through a cross-sectional area A1, but by the time the fluid has reached the right-hand portion of the pipe, okay, the cross-sectional area of the pipe is decreased, okay, to a value A2. When we talk about the flow rate, and we'll start by trying to describe the volume flow rate, okay, by definition, the volume flow rate tells us the volume of fluid, okay, that passes a given point in the pipe per unit time, let's say delta T. Okay, so if we want to look at the volume flow rate, let's say over at point 1 right here in the pipe, we're really talking about what is the volume of the fluid that passes point 1 in a given time, delta T. Okay, the amount of volume passing that point in the pipe per unit time. Well, hopefully you can see when you look at the diagram here that the volume of fluid passing point 1 right here, okay, in a time delta T, we could say would be equal to the cross-sectional area of the pipe here, A1, okay, times delta L1. A1 times delta L1 gives us that volume, okay, and as long as we are talking about that volume, okay, moving past point 1 in a time delta T1, okay, then this ratio here would give us an expression for the volume flow rate. When you take a look at delta L1 over delta T1, okay, what does that really measure? Well, hopefully you can see that if we say, the fluid moves a distance delta L1 in a time delta T1, what that really is a measure of is fluid speed. So we can write that ratio delta L1 over delta T1 as V1, really the speed of the fluid, okay, at point 1 there. So here we have an expression for the volume flow rate. Okay, the volume of fluid flowing past a given point in a pipe, let's say, per unit time. It is simply equal to the product of the cross-sectional area of the fluid, okay, times the speed of the fluid. Now, if we want to talk about the mass flow rate, okay, it's very much the same concept. We're really talking about the mass of fluid, let's say delta M, that passes a given point in the pipe per unit time delta T. So going back and looking at our same diagram, our same pipe here, okay, we can see that the mass of fluid flowing past point 1, well, it's related to the volume of fluid passing point 1, okay, using this concept of density. So, okay, this volume of fluid here we use to calculate the volume flow rate has a certain mass, okay, given by the density of the fluid times that volume. Okay, so rho 1, okay, times delta V1 is the mass of the fluid passing point 1, delta T1 the time it takes that mass to pass point 1. Okay, so when we look at the dimensions here, the volume of fluid, as we said previously, is just the cross-sectional area times the length. And as we said previously, this ratio delta L1 over delta T1 simply gives us a measure of fluid speed, okay, how fast the fluid is moving, okay, at that point in the pipe. So when we simplify here, we end up with this expression for the mass flow rate. Notice that it looks very similar to the volume flow rate, okay, with the exception that we are now multiplying by this constant rho, that is the density of the fluid, okay, at that point. Now that we've talked about the concept of flow rate, we can state the equation of continuity as it applies to moving fluids. We'll begin with a very general statement for the continuity equation, okay, that applies to all fluids. Simply stated, we can say that the mass flow rate is constant. Now, to apply this in a problem-solving environment, a more useful formula would be to say that the mass flow rate at one particular point in your moving fluid must be exactly equal to the mass flow rate at a second point in the moving fluid. So plugging in our previously derived expression for mass flow rate, we can say that okay, rho 1 times A1 times V1, representing the mass flow rate at point 1 of the fluid, must be equal to rho 2 A2 V2, okay, which represents the mass flow rate at a second point in the fluid. Now, this statement here, this applies to all fluids, okay, whether they be liquids, gases, or plasmas. If you're dealing with a problem involving gases or plasmas where the fluid density is not constant, then this is the equation that you must use, okay, for continuity. In the special case of incompressible fluids, okay, where the density is constant, and remember this is not a good approximation for gases, but it is a good approximation for liquids, okay, which we say are fairly incompressible. Okay, so for that special case, we can then take it a step further and say that the volume flow rate is constant. Okay, where we can then say the volume flow rate at one particular point in a fluid, okay, must be exactly equal to the volume flow rate at a second point in the fluid. Okay, and plugging in our quantitative expression for volume flow rate, okay, we can say that A1 V1 must be okay, exactly equal to A2 V2. Okay, what is the physical justification for the equation of continuity? Well, when you think about it, the equation of continuity is really nothing more than a statement of the law of conservation of mass as it applies to fluid flow. If the continuity equation were not true, then that would imply that the mass of the fluid flowing through a given cross-section per unit time would vary, okay, implying that the mass would not be conserved, okay, that there could be sources or sinks in the fluid, okay, that mass could either be created or destroyed, okay, as the fluid moves. And we know that that simply cannot be the case. So the law of conservation of mass proves to be the physical justification, okay, for the equation of continuity for moving fluids. So we'll look at a few examples to see what the continuity equation tells us about the nature of fluid flow. We'll look at a couple of qualitative problems as well as a quantitative example. So in the first example, it says river varying width. What happens to the water speed when the river narrows? Well, you don't have to take a physics class to know this, okay, but let's see how the continuity equation predicts, okay, the result here. So we say that if the volume flow rate is constant, okay, and if we're talking about a liquid, we can use the volume flow rate as opposed to the mass flow rate. If the volume flow rate is constant in time, this tells you that as the cross-sectional area gets smaller, as the river narrows, then the fluid speed must get bigger, that there is this inverse relationship between the cross-sectional area and the fluid speed, okay, in order for the flow rate to remain constant. So like I say, this applies to pipes, rivers. You know that when a river narrows, okay, that's where your rapids are going to be. That's where the speed of the water is going to be the greatest. The adjustable shower head. How is the speed of water coming from the holes in the shower head controlled? Okay, it's a simple matter of cross-sectional area. So you can see here that by decreasing the cross-sectional area of the holes, that is the total cross-sectional area of the holes, the speed of the water leaving the holes will increase. So you know that in your adjustable shower head, if you want to put it on the massage setting where you have a high fluid speed, you're going to have a far fewer number of holes so that the total cross-sectional area of the water coming out of those holes will go down. Let's take a look at a quantitative example here. So arteriosclerosis, we're told that blood normally flows with an average speed of about 10 centimeters per second in the large arteries, okay, having a radii of about 0.3 centimeters. Okay, suppose that a small section of an artery is reduced in radius by 1/2 because of a thickening of its walls. Okay, calculate the blood speed past the constriction. So as the simulation shows you here, okay, looks like we've got some arterial plaques building on those walls, which are going to decrease the cross-sectional area. And here we're told that the radius decreases by 1/2. Okay, what's going to happen to the speed of the blood in that region of the artery? So once again, we're dealing with a liquid, so we can use the equation of continuity expressed in terms of volume flow rate. And here, okay, if we think of a circular cross section, then we'll use the area of the circle being pi r squared. And when we plug in the numbers here, okay, the pi's will cancel out on both sides of that equation, okay, but we're told that if the radius of the healthy portion of the artery is 0.3 centimeters on the left, okay, and that radius gets reduced by a factor of 1/2 here on the right, okay, it'll be 1/2 of 0.3, and don't forget to square it. We know that in the healthy region, the fluid speed is 10 centimeters per second. So what happens here when we solve for V2 in the constricted region of the artery? And when we do this, we get a speed of 40 centimeters per second. So you can see here, you know, the danger with arterial constriction, I should say, that the radius decreases by a factor of 2, but the fluid speed increases by a factor of 2 squared, or 4. We'll see later on when we talk about Bernoulli's principle why this is so problematic for blood flow in the arteries. So this brings us to Bernoulli's principle, a very important physical principle that tells us the relationship between fluid speed and fluid pressure. Later in the presentation, we'll see that it is really nothing more than the law of conservation of work energy applied to the special case of fluids. But first, we'll start by looking at Bernoulli's principle in a qualitative fashion to explain many naturally occurring phenomena. So after that, we will derive the Bernoulli equation that will allow us to obtain quantitative information about phenomena, and subsequently take a look at how to apply the principle in solving various quantitative problems. Okay, but let's not get ahead of ourselves here. Okay, qualitative treatment in this slide and some upcoming slides. So Bernoulli's principle can be stated as follows. Okay, we can say that where the velocity of a fluid is high, the fluid pressure is low. And where the velocity of the fluid is low, the fluid pressure is high. Okay, said symbolically, we can say that there is an inverse relationship between fluid pressure and fluid speed. So that's what we suggest with this relationship right here. Okay, inverse relationship between fluid speed and fluid pressure.
We're going to take another look at a very cool demonstration involving Bernoulli's principle in a ping pong ball. What I have here is a funnel attached to the end of this tube, which is attached to a source of air. And this source of air, well, blows air out from the funnel. We turn it on here, and you'll see when I hold this piece of paper, okay, that air is being blown out from this funnel. What I'm now going to do is take a ping pong ball and I'm going to put it at the base of the funnel when I hold it vertically. Let's take a look at what happens. Even though air is being blown out from the stem of the funnel, that ping pong ball is not being forced downwards in the direction of gravity.
So to try and explain why this ping pong ball remains in the funnel when air is blowing in the direction of gravity, okay, let's take a look at a few of the streamlines surrounding the ball. Okay, what you can clearly see by the white streamlines in this illustration is that in the region above the ball, okay, the air is moving quite fast there. Okay, shown by the fact that not only the streamlines exist, but they're quite close together. In other words, okay, we have a high fluid speed, and according to Bernoulli's principle, we should have a low fluid pressure in that region. Notice now that in the region below the ball, there's not a lot of moving air there. Okay, and in that case, we would have a low fluid speed and a much higher fluid pressure. So you can see that a pressure gradient or pressure difference exists across the ball, okay, shown with these red arrows in the figure. Okay, because of the fact that we have a higher pressure, okay, a higher fluid pressure below the ball than above it. So, okay, you know that the pressure is directly proportional to force. So this pressure difference or pressure gradient provides us with a net upward force that keeps the ball in equilibrium in the funnel.
Now this one I call blowing between the sheets. And this is something you can do at home if you've got a couple pieces of paper. Okay, hold two pieces of paper in each hand and blow right between them. And notice what happens. Pieces of paper come together. If you only have one sheet of paper handy, well, you can do a similar demonstration, have just as much fun. Okay, take a piece of paper and blow right across the top surface of the paper and notice what happens. Okay, we can get that piece of paper to rise. Let me do it from a side view here. We can get that piece of paper to rise right up against the force of gravity. To explain this, we need to know a little bit about Bernoulli's principle.
So let's see how Bernoulli's principle can once again be used to explain this demonstration. Okay, what can cause the piece of paper to rise up against the force of gravity. And what I'm hoping is that you're going to start to see a pattern in these slides and see how similar, for example, this demonstration is, okay, really the explanation for this demonstration is to the case of the ping pong ball in the funnel. Okay, so what I'm showing you here is a side view of the sheet of paper. We'll choose to simply look at the single sheet of paper and attempt to explain what makes this paper rise up against the force of gravity. So, okay, here is our air source and here is our air stream. In this case, provided by the blow dryer you see in the figure, but of course in the demonstration it was provided by my mouth. Okay, my mouth blowing air across the top of the piece of paper. Notice that these green streamlines represent the path of the moving air, okay, above the piece of paper. So, how would we explain this rising action against the force of gravity? Well, this region above the piece of paper represents a region where the fluid speed, that is the air speed, is high. Okay, and therefore, according to Bernoulli's principle, okay, where the air speed is high, the air pressure is low. Okay, in general, where the fluid speed is high, the fluid pressure is low. When we look at the region below the piece of paper, notice that there's very little moving air there, right? I mean, I was only blowing air above the piece of paper. Okay, in which case, with very little moving air below the piece of paper, we can say that the fluid speed, the air speed is quite low there, and therefore, according to Bernoulli's principle, the air pressure would be much higher there. So once again, you can see that a pressure gradient gets set up. Okay, a lower pressure above the piece of paper pushing it down, okay, a higher pressure below the piece of paper pushing it up. And once again, okay, this pressure difference or pressure gradient translates into a net upward force, okay, that will cause the piece of paper to rise.
So we're going to take a look at the physics behind an atomizer, like a perfume atomizer. Have you ever wondered how a perfume atomizer is able to shoot perfume out of a bottle that is not pressurized? Okay, well, the atomizer makes use of Bernoulli's principle. But rather than shooting perfume out of our atomizer, we're going to shoot Rice Krispies so we can actually see the effect. Now, the operation of an atomizer, I'm going to take this tube here, and all I'm going to do is I'm going to blow air across the top of the tube. According to Bernoulli's principle, if I look at the air that's moving over the top of the tube, it's moving quite fast, and where the air speed is high, the air pressure in that region is low. Down here where the Rice Krispies are, there's very little moving air. The airspeed is low, and therefore the pressure is high. Because we have a difference in pressure between the bottom of the tube and the top of the tube, okay, the air and the Rice Krispies are going to move from the low pressure region to the high pressure region. So let's see Bernoulli's principle in action and see how the atomizer works. Take my air source, I'm simply going to blow air across the top surface of that tube.
So let's use Bernoulli's principle to try to explain the physics behind the atomizer. So in this illustration here we have our cup full of Rice Krispies. Okay, and here's our vertical tube that is placed inside the cup. Okay, along with the air source that is blowing air across the top end of the tube. You see the pink streamlines above the tube where we can assume that we have a high fluid speed and according to Bernoulli's principle, therefore a low fluid pressure. Okay, notice that in the region at the bottom end of the tube where the Rice Krispies exist, okay, that represents a region where there's really not much moving air, so we have a low fluid speed there, okay, and according to Bernoulli's principle, a much higher fluid pressure. So once again, you see that a pressure gradient, a pressure difference gets set up across the tube, okay, which translates into a net force, okay, that will cause those Rice Krispies to move from the high pressure side at the bottom of the tube, okay, to the low pressure side at the top of the tube. So in this slide, we'll see how Bernoulli's principle can be used to explain the very nature of flight. Now, I want to be really clear that if you look at that big old jet airliner, that 747, and you're wondering how is it that a fully loaded massive airplane like that can get off the ground? Well, Bernoulli's principle does come into play, but Bernoulli's principle alone could never explain how a fully loaded large aircraft is going to get off the ground. It has more to do with Newton's third law. But let's take a look at the Bernoulli effect. And I will say it comes into play much more when we talk about, let's say, fighter planes, which can move quite fast, okay, and are much less massive. So in order to see the Bernoulli effect, we need to take a look at a cross-section of an airplane wing, okay, or a bird wing. And we see that it has this characteristic shape. It is not flat. Okay, so the curvature of the wing forces the air moving above the wing to travel a greater distance over the wing, okay, in a given time period, thus making the air moving above the wing travel faster than the air moving below the wing. So you can see here in this diagram that these air streams, okay, would then suggest that there's going to be this pressure gradient. So let me show you in this cross section of the wing here that I can control a little bit better. I'm showing you some of the air streams in blue. You can clearly see that the air traveling above the wing travels a greater distance, okay, in the same time, meaning it travels faster. So the fluid speed above the wing is high, okay, generating a low pressure region, okay, whereas below the wing where the air is traveling slower, okay, the fluid speed is less, meaning the fluid pressure there is higher. Once again, we see that this pressure gradient, okay, translates into a net upward force that we call a lift force on the wing.
So we're going to take a look at the physics behind the curveball, sometimes called the Magnus effect, which is really just a phenomenon of Bernoulli's principle. When we talk about the curveball, what we have is we have a ball which is moving through the air, and in addition to the forward motion of the ball is given a spin. Okay, and as we'll see, because of that spin and its forward motion, a low pressure region develops which causes a sideways or deflecting force on the ball, which makes the ball curve, so to speak. Now, because we cannot slow down the motion of this ball, we're going to use this apparatus right here to simulate the curveball. With this apparatus here, rather than throwing it through the air, what we're going to do is we're going to take a source of air and force the air past this vertical cylinder. That is going to simulate the forward motion of the ball. To get the spin, I'm going to pull on this cord and I'm going to cause this thing to rotate. So this cylinder is going to have rotational motion, it's going to spin, in addition to having air moving past it. And what we're going to see is that there's going to be a sideways or deflecting force on it, which is going to make it move to the side. In the same way, we have that deflecting force on the baseball that causes it to curve. So let's get this going here. I'm going to pull on the string to cause the spin. Okay, let's activate the air source here. Notice when I blow that source of air, okay, it causes it to move to the side. The simulated curveball, folks.
Now, let's see how Bernoulli's principle can be used to explain the physics behind the curveball, sometimes known as the Magnus effect. What you see here is the baseball with its seams, and in this picture we're looking at a top-down view, let's say an airplane view of the ball. The curveball happens because the ball is made to spin in addition to moving forward. So in this picture here you see the velocity vector representing the motion of the ball forward, but you also see the red arrows suggesting the direction of the ball's spin. Now, from the point of view of the ball, we can show the streamlines. We can see the air that is moving past the ball as it travels. And what we're going to do is we're going to take a look at the effect of the spin. That spin causes a boundary layer of air in contact with the seams of the ball to move more rapidly on one side of the ball than the other. So let's look at a point on really the left-hand side of the ball, which is on the top part of your computer screen, as compared to the point on the right side of the ball, which is really on the bottom portion of your computer screen. We'll look at these 2 points. Now we really have 2 velocity effects. The first is due to the forward motion of the ball. And from the point of view of the ball, we can say that the air is rushing past it, as you see with these 2 velocity vectors. But in addition to the forward motion of the ball, we have the spin of the ball. And when we represent those velocity vectors, we see that on the left-hand side of the ball, that's the upper portion of your computer screen, because of the direction of the spin, the air actually is moving opposite the air due to the forward motion of the ball. On the right-hand side of the ball, that is the bottom portion of your screen, you see that the air there is moving in the same direction as the air due to the forward motion of the ball. So what happens there is that we have, when we look at the vector sum, on the left-hand portion of the ball, that is the top portion of the computer screen, we see that the spin effect cancels out some of the forward motion effect, giving us a smaller air velocity there. On the right-hand side of the ball, the bottom portion, in that case, the moving air due to the spin goes to reinforce the forward motion of the ball. Those velocity vectors are in the same direction, giving us a larger air speed there. So what we get then is that on the left-hand side of the ball, that's the top portion, we have a lower fluid speed, lower air speed, and consequently a higher fluid pressure. On the right-hand side of the ball, the bottom portion of your computer screen, we have a higher fluid speed and therefore a lower fluid pressure. This causes a pressure gradient to exist across the ball, and that pressure gradient in the language of force gives us a deflecting force acting on the ball, as shown with the green arrow. So that in addition to the ball moving forward, that deflecting force causes the ball to curve.
In this slide, we'll see how Bernoulli's principle can explain the very survival of underground mammal dwellers. You know, those cute little gophers and moles that tear up your garden or lawn. So as you can see here in the diagram, okay, in this case, we're talking about prairie dogs. Okay, you can see that they construct their burrows with multiple openings at different elevations. Okay, the reason for this is that airspeed is dependent upon elevation. So according to Bernoulli's principle, having different air speeds at different openings will cause a pressure difference a pressure gradient across the opening, allowing air to flow from the high pressure opening to the low pressure opening, thus causing the needed air circulation for survival.
Bernoulli's principle can be used to explain housing design as well as problems that houses encounter in high wind areas, such as areas there are hurricanes. Why are rooftops inclined to pop off rather than blow off in a hurricane? As we'll see, when you see pictures of hurricanes that have hit certain areas, and when houses end up losing their roofs, a common misconception is that the sheer force of the wind blows these roofs off the houses. But as we'll soon find out, it's really not the force of the wind that blows the roof off the house. It's really a difference in pressure that causes the roofs to pop off of a house. So to see this phenomenon, we'll start by taking a look at airflow on the top surface of the roof during a hurricane. Notice that if the doors and windows are closed, there is very little airflow inside the house, but with high wind speeds, we have a great deal of airflow and high wind speeds on the roof of the house. The differences in airspeed between the inside and the outside of the house cause a pressure gradient to develop. And as we see, according to Bernoulli's principle, the high fluid speed on the top of the roof on the outside causes a low fluid pressure there. And inside the house, where there's very little moving fluid, we have a low fluid speed and a high fluid pressure, causing a fluid pressure difference, a net force causing the roof to pop off. So that might lead us to ask the question, what would you think would be the ideal design for a rooftop in a hurricane area? Well, as you see in the picture here, the peaked roof acts like the top surface of an airplane wing. It actually causes a greater fluid speed. A flat roof is advantageous because we would have a lower speed on the surface of a flat roof than a curved or pointed roof.
So have you ever noticed when taking a shower in a stall with a shower curtain as opposed to a glass door per se, that very often when you turn the water on in the shower, that shower curtain gets drawn up to your body? Okay, you have a sticky shower curtain. Well, this can be explained very simply using Bernoulli's principle. That in the region inside of the shower where you have a moving fluid, okay, that is water, where the water speed is high, okay, this creates a low pressure region on the inside of the shower compared to a higher pressure region outside of the shower where there is no moving fluid, no moving water. And of course, this difference in pressure, this pressure gradient, can result in a net inward force. So we're going to use Janet Leigh here in the Alfred Hitchcock thriller Psycho of 1960 to illustrate this. Okay, you will notice that when she turns on the water, okay, that high fluid speed causes a net inward force, okay, that causes the inward motion of the shower curtain. So we see that Bernoulli's principle can be used to explain a very common cause of heart attacks due to arterial blockage. So what I'm showing you in the diagram here of the artery is you will see this arterial plaque which is attached to the arterial wall. And you'll notice that because of the formation of that arterial plaque, it causes a constricted region in the artery, okay, where the cross-sectional area has been reduced. And according to the equation of continuity for fluids, okay, this constriction, okay, this reduced cross-sectional area should lead to a higher fluid speed, higher blood speed in that region of the artery. So we notice that, Okay, in this region above the plaque here, right near the arterial wall, there's very little moving fluid, very little moving blood there, okay, which would suggest that the blood pressure there should be higher than in this constricted region below the arterial plaque, okay, where the blood speed should be high, okay, creating a lower blood pressure there. So once again, as we see, okay, this pressure gradient, this pressure difference, okay, set up across this arterial plaque can translate into a net force that can dislodge the plaque from the arterial wall, causing it to move downstream and potentially causing an arterial blockage that would lead to a heart attack. I think at this point we've seen enough examples to see how this inverse relationship between fluid speed and fluid pressure can cause pressure gradients and net forces on objects in moving fluids, okay, causing these objects to change their state of motion or accelerate. But we now want to be more quantitative in our use of Bernoulli's principle so that we can answer questions like, how fast is a fluid moving in a given region? Or what is the fluid pressure in a region where the fluid is in motion? In this slide, we're simply going to state what we call Bernoulli's equation. Okay, while in the next slides, we'll actually see where it comes from by deriving it. So for now, we can state Bernoulli's equation as follows. Okay, in a region where we have a fluid, okay, we have these three terms here. P, capital P represents the fluid pressure in that region. Okay, this term 1/2 rho v squared. Okay, rho being the fluid density, v being the fluid speed in that region. Okay, plus rho gy. Okay, again, rho being the fluid density, y being a measure of height above some reference height. Okay, in the same way when we talk about gravitational potential energy, okay, we talk about the height of an object above some reference height, whether the surface of the earth, okay, the center of the earth, a table. Same thing applies here. One thing you'll notice is that that second term kind of looks a lot like kinetic energy term if we were to replace density with mass. And that last term, okay, rho gy, looks an awful lot like a gravitational potential energy term, once again, if we replaced, okay, the fluid density with mass. It's important to note here that all these three terms, if we look at their units, okay, would have units of pressure. So each of these terms represents a measure of pressure. When it comes to solving problems, a more useful form of this equation, okay, can be written as follows. And the reason for this is that when we talk about the sum of these three terms being equal to a constant, that constant is going to vary from problem to problem. So a more useful form in problem solving would be to make a comparison, okay, of these three terms at two different points in a fluid. Okay, we can say that, subscript 1 represents one region in a fluid, subscript 2 represents a different region in the fluid, and since the sum of these terms is a constant, okay, we can say that the sum of these terms in one region must equal the sum of these terms in another region. In that sense, we don't have to actually know the value of that constant, which, like I said, is going to be dependent upon the particular problem we're solving. Hopefully you're realizing in our study of fluid mechanics so far, there's no new physics here. All we've done thus far in talking about fluids is to apply the laws of mechanics to the special case of fluids. Bernoulli's equation is nothing more than a statement of work energy conservation for fluids, as we'll soon discover. So in the next two slides, we're going to apply okay, the physics you already know, okay, physics you learned in your course in mechanics, we're going to apply that in order to derive Bernoulli's equation. Okay, the fun of being in an engineering level physics course. So let's get started here. We're going to consider the flow of an ideal fluid through a non-uniform pipe, okay, where a small volume of fluid has been effectively transferred from a lower position to a higher position. So in our diagram over here, you see down at the lower position, we're going to look at the small volume of fluid, okay, described by the cross-sectional area A1 times the length of the fluid segment delta x1. We're going to take that volume, which starts out at a height y1, okay, and we're going to effectively move it, okay, up to a higher position y2, as you see here. So we're going to start by calculating the net work that is done on this fluid. Notice here that what is it that's going to make this fluid move from the lower position to the higher position? Well, what I'm not showing you is the pipe to the left of this small volume here, okay, and there's fluid in that pipe, and that fluid exerts a pressure, okay, on the small volume of fluid that we're considering here. So there is a forward pressure that, okay, does work on that small volume of fluid, okay, to move it from the low position to the high position. Likewise, when we take a look at the pipe up here, okay, there is also a backward pressure from the fluid to the right of this volume here that I'm not showing you, that is supplying a backward pressure on the fluid. So when it comes to calculating the net work, using our definition of work, right, okay, magnitude of force times magnitude of displacement times the cosine of the angle between the force and the displacement, okay, you can see here that, okay, F1 represents the force due to the fluid pressure to the left of this fluid element, okay, delta x1 represents the distance, okay, that volume of fluid moves, and because the force acts in the same direction of fluid motion, okay, the angle between the force and the displacement is 0 degrees. That's where this cosine zero terms comes from. Okay, when we look at, okay, the fluid in the higher position up here, okay, we can see that the fluid to the right exerts this backward force, okay, due to the fluid pressure we'll call F2. Okay, in this case the fluid has to move to the right a distance x2 and being transferred from the low position to the high position. But in this case, okay, that backward force due to the fluid pressure, okay, gives us a cosine 180 degree factor because the force and the displacement, that is the force acting to move the fluid to the right, okay, is actually opposite the displacement of the fluid to the right. Okay, in other words, you see here that the force actually acts to the left while the fluid moves to the right. So we can evaluate the cosine 0, cosine 180 degree terms, in which case our expression simplifies to this. And now we're going to substitute the language of fluid mechanics in here. Okay, remember we say that the force due to fluid pressure is simply the pressure times the area. This comes from our definition of pressure. So we'll substitute that in. And finally, we will use the fact that since we're talking about a liquid here, okay, we see here that this fluid volume here, A1 delta x1, is nothing more than this fluid volume we're considering here. So here delta V1 is given by the cross-sectional area A1 times this length delta x1, and the volume up here, okay, is given by the cross-sectional area, the different cross-sectional area here, A2, okay, times this length here, delta x2, which represents the distance the fluid moves at that point as well. Okay, and finally, since we're considering a liquid, and liquids are fairly incompressible, we can then say that delta V1 equals delta V2. So that allows us to simplify the expression, okay, to this. Next up, we're going to calculate the change in kinetic energy for this moving fluid. And here we know our expression for kinetic energy, 1/2 mass times speed squared. Okay, and we can substitute the fact that in the language of fluid mechanics, the fluid mass is given by the fluid density times the fluid volume. Okay, and remember that since the volume of fluid is the same, okay, we can say the mass of the fluid is the same as well, okay, given by this expression rho delta V. So here we end up with an expression for the change in kinetic energy of the fluid as it moves from position 1 to position 2. Okay, just like we said, the net work in this expression here represents the net work done on that fluid as it moves from position 1 to position 2. All right, so in this slide we will finish our derivation of Bernoulli's equation. Okay, you recall from the previous slide that we applied the work energy theorem to a segment of fluid, okay, in this fluid-filled pipe here. And we said that the net work done on that fluid segment was exactly equal to its change in energy. Okay, and we calculated the net work done on this segment of fluid, okay, due to external forces, that is due to the fluid to the left of it, okay, that is pushing it to the right, as well as to the fluid to the right of it here that is pushing it to the left. So we calculated the net work done in moving this segment of fluid from position 1, this low position at Y1, to this higher position at Y2. We also calculated the change in kinetic energy of the fluid, okay, as it moves from position 1 to position 2. Remember, the equation of continuity tells us that, okay, the cross-sectional area of the pipe, okay, will affect the fluid speed. So we would expect that there's a change in kinetic energy, okay, due to the change in cross-section of the pipe. All we have left to do is to calculate the change in gravitational potential energy of the fluid as it moves from the low position, okay, to the higher position. So the change in gravitational potential energy will symbolize delta U, and we know from mechanics that, okay, gravitational potential energy goes like the mass, okay, of our object times acceleration of gravity times, okay, y or h, which represents a height in a gravitational field above some reference height, some 0 point of height. Okay, and here, since we are moving our fluid from a starting position at y1 to an ending position at y2, this expression gives us the change in gravitational potential energy of that mass of fluid as it moves from, okay, position 1 to position 2. In the language of fluids, we can represent the segment of fluid rather than describing it in terms of its mass m. We can write it in terms of, okay, its density times volume, okay, which is an equivalent expression for mass. So here we have an expression for the change in gravitational potential energy as that fluid moves from its low position, position 1, to its higher position, position 2. We're now in a position to, okay, combine all of our work on this slide and the previous slide, okay, substituted into the work kinetic energy theorem here. Remember that the work energy theorem, or sometimes called the work kinetic energy theorem, simply tells us that the net work done on a system is exactly equal to its change in energy. The energy can take on the form of kinetic energy if there's motion involved, okay, or it can take the form of changes in potential energy. For mechanical systems, remember that the change in potential energy we're talking about, okay, is going to be gravitational potential energy, possibly elastic potential energy, but in the case of fluids, it's going to be represented by a gravitational potential energy term here. So let's substitute our previous expressions into the work energy theorem here. And we see here that, okay, from the previous slide, this term right here, okay, is nothing more than the net work done on that fluid by external forces, okay, really the force from the fluid to the left, okay, which pushes it to the right and upwards, okay, the opposing external force from the fluid to the right, okay, which is impeding its motion, pushing it backwards, okay, but this expression gives us the net or total work done on that fluid and moving it from position 1 to position 2, okay. Here we see this expression here simply tells us the change in kinetic energy of that fluid as it moves from position 1 to position 2. And this last expression here simply tells us the change in gravitational potential energy of that fluid segment as it moves from position 1 to position 2. You'll notice that in all of these terms, there is this common factor delta V for the fluid volume. When we divide both sides by delta V and eliminate that term, our expression simplifies to this. And you'll notice that in so doing, we end up moving from expressions of work and energy to expressions of pressure. Notice here that, okay, the left-hand side here, P1 minus P2, this tells us, okay, the pressure difference, okay, due to those external forces, due to that net force, okay, acting on this fluid segment. Okay, and we know that you know, these terms here on the right, 1/2 rho V2 squared minus 1/2 rho V1 squared, these terms also represent pressure terms, okay, and as we said, when a fluid moves, okay, that affects the pressure. So these two terms here tell us the difference in pressure, fluid pressure, due to the fluid motion, due to the fact that the fluid is moving at different speeds in each of these two regions, region 1 and region 2. So this tells us that the pressure difference due to the speed difference. And lastly here, we know from our previous lecture on fluid mechanics that fluid pressure increases with depth. Okay, so here, this, what started out as a gravitational potential energy difference now really gives us a pressure difference, okay, due to different depths in the fluid. So, you know, when we're talking about a fluid and we're talking about region 1 and region 2, okay, different depths in a fluid, okay, will give us different pressures, as you can see in this expression. To turn this into a more workable or useful equation when it comes to problem solving, all we're going to do is rearrange these terms, okay, put all of our terms with 1's on one side of the equation and 2's on the other side of the equation, okay, and this basically tells us here that the fluid pressure in region 1, okay, plus, okay, this expression telling us that relates fluid pressure to fluid speed in region 1, plus this expression here, which relates, okay, the fluid pressure due to fluid depth in region 1, okay, that the sum of these terms must be exactly equal to the sum of those three terms, okay, in a different region of a fluid. So this is Bernoulli's equation that will be quite useful in problem solving, and we will apply this to some problems in the upcoming slides. Let's now apply Bernoulli's principle to a couple of examples. we'll return to the case of the sclerotic artery that we looked at previously to get some quantitative information about these arterial plaques. So in this problem, we're told that blood having a given density flows through an artery which is obstructed with a plaque attached to the arterial wall. And that where this plaque exists, the cross-sectional area of the artery has been reduced to 1/5 of its normal cross-sectional area. The bottom surface of the plaque, we're told, okay, has a given surface area, and we're assuming that the top surfaces in the channels, okay, have about the same surface area. We're asked to calculate the net downward force acting on the plaque that tends to dislodge it. So Bernoulli's principle doesn't tell us about force directly, it tells us about pressure. But knowing what we know, okay, previously here, okay, from the example we looked at, we see that qualitatively speaking, because of the constriction in the artery, according to the equation of continuity, the blood speed is going to increase in the constricted region due to the decrease in cross-sectional area, and that increase in blood speed should cause a decrease in blood pressure there. Okay, compared to the region above the plaque over here at point 1 in the diagram, where there's virtually no fluid speed and a much higher fluid pressure. So we're going to make the assumption that the speed of the blood here at point 1 is about 0, since there's really nowhere for it to go. So let's get started here. To apply Bernoulli's principle, we need to know the fluid speed at the 2 points we choose. Okay, so we're going to choose point 1 here and point 2 when we apply Bernoulli's equation. But first, to get the fluid speed at point 2, we're going to use the equation of continuity, okay, at what I'll call point 0 over here in the healthy region of the artery to figure out that blood speed. So since we've done this previously, we'll do it very quickly here. Okay, and the healthy cross-section of the artery has 5 times the cross-sectional area as the obstructed portion. So when we find the fluid speed here in the constricted portion of the artery at position 2, okay, then that speed should be 5 times, okay, the speed in the healthy portion, which gives us a speed of, okay, about 25 centimeters per second or 2.5 meters per second. All right, so we're now in a position to apply Bernoulli's equation. And we're going to make the assumption that in comparing point 1 in the artery here to point 2, while there clearly is a difference in height, that difference in height amounts to maybe a couple millimeters. It's a very small difference, and in terms of this gravitational potential energy and pressure, it's a difference that is not worth investigating. Its contribution is insignificant. So we're going to consider these to be about the same heights. Now, clearly, if we were told that we're going to compare 2 regions in an artery, let's say between an artery in a person's head versus foot, then we're talking about a difference in height of a meter or more. In that case, we should take into account the differences in the gravitational potential energy. So here's an expression for Bernoulli's equation. Okay, we've solved it for the pressure difference here, because this pressure difference, remember, is going to give us a net downward force. It's going to dislodge that plaque. And we'll notice here that when we plug in the numbers here, okay, rho, the density of blood is given. We found out the blood speed at position 2 in the artery here, okay, from the equation of continuity to be 2.5 meters per second. Remember, we assumed that the speed of the blood here at position 1 is virtually 0. And given the fact that y1 is about equal to y2, there's no these potential pressure turns turn to 0. We do the number crunching. We get a value of about 3,200 pascals. That is the pressure gradient, okay, that tends to push this plaque downwards into the artery. And if we want to find the net force, okay, then the net force is simply that pressure difference or pressure gradient times the area, which is given to us in the problem. okay, half a centimeter squared, which we'll convert over here to MKS units, gives us a value of about 0.16 newtons. Now, just to point out here, 0.16 newtons, that may seem relatively small to you, but remember that if I said the weight of a very tiny apple is about a newton, this is about the fifth of the weight of an apple, and we're talking about a very small system like an arterial plaque attached to a wall. That represents a fairly sizable force that can clearly dislodge that arterial plaque and, potentially cause a heart attack. So doing a problem like this, it kind of makes you want to go out and order a nice, juicy, fatty hamburger, doesn't it? So in this last example we'll look at, this is sometimes referred to as Torricelli's theorem. It actually, we will derive, it is a special case of Bernoulli's principle. And we will see that in the next slide, it is the physics behind how a siphon works. Okay, but starting in this problem, we're told that consider a 2-liter Coke bottle with a hole in the bottom. Okay, when the top cap is removed, okay, with that hole in the bottom, okay, which we are told here is 20 centimeters beneath the surface of the liquid here, okay, that is going to cause, in this case, Coke to come out of the hole at a certain speed. So in this problem here, we are asked to find out what is the speed of the Coke emanating from that hole that is 20 centimeters beneath the surface of the fluid, okay, at least to start out the problem. So obviously as that fluid leaves, that 20 centimeters is going to get smaller in time, in which case the fluid speed will get smaller as well. We're really asked to find the fluid speed right at the start of the problem. So here's a case where we're going to apply Bernoulli's equation, and to apply Bernoulli's equation we need to choose those 2 points in our fluid where we evaluate these pressure terms. So we're going to consider the top surface of the fluid to be 1 point, and the bottom surface, which is where we're asked to find information, okay, that will be where the hole is, that will be the second point we choose. So here we're going to make the assumption that, okay, the fluid speed up at the top surface, okay, up here, is going to be virtually zero. Okay, notice we're not given a value for it in the problem, but you've probably seen the equivalent of this many times in your life, that over here we can say that the fluid speed is virtually zero compared to the speed of the fluid where the hole is. It's an approximation we'll make. And when you solve Bernoulli principle problems, you very often have to be thinking to make approximations like this, especially when the information is not given in a problem. Is the fluid speed there exactly zero? No, but think about the fluid speed there compared to the fluid speed at the other point you choose, and we see that it's virtually insignificant. So we're going to choose the hole as the 0 point to measure our height. Okay, we will assume that at this hole here, that's height 0, and then at the top portion of the fluid, that is going to be at a height of 20 centimeters or 0.2 meters above, okay, our bottom point, our second point. So we're now in a position to apply Bernoulli's equation to find the speed of the fluid at the bottom point, at the hole. There's a statement of Bernoulli's equation. Notice instead of using 1s and 2s, I've substituted the subscripts T and B for bottom. This is always a good idea because when you're using subscripts that don't make a lot of sense for the problem, it's easy to get quantities confused. So my recommendation is always is try your best to choose subscripts that will help you remember. It's one less way you got to worry about making a mistake when you solve these problems. And here, when we evaluate the terms here, okay, notice that at the top surface of the fluid here, okay, the pressure, the external pressure is simply that of air above it. In other words, atmospheric pressure. Okay, so here at the top surface of the fluid, the Coke, okay, that external pressure is atmospheric pressure. Notice here where the hole is, that portion of the fluid also is exposed to the atmosphere. So the external pressure there, okay, is also simply atmospheric pressure. We already said that the fluid speed at the top here, the Coke is not moving there, so that's why we have the 0 here. When we put in this gravitational potential energy term, okay, Coke is about water. It's got some sugar in it. Its density is probably a little bit greater than 1,000, but not much. Okay, times G times the height we said was 0.2. Fluid speed at the bottom here, okay, this term 1/2 fluid density times fluid speed squared, that's what we're trying to find, that's our unknown in the problem. Okay, and then remember we said that the bottom of where the hole is, that's what we arbitrarily determined to be height 0, so there is no y value there, there's no height there. And when we do the number crunching, we solve for V2, okay, we come up with I should say V bottom, we come up with this expression here, okay, that the speed there is simply equal to the square root of 2 times the acceleration of gravity, okay, times the difference in height, okay, which is 0.2 meters, gives us a fluid speed of 2 meters per second. So the square root of 2g height factor, that's what we call Torricelli's theorem. Right, and lastly, we'll see how Torricelli's theorem can be used to predict, okay, or explain the action of the siphon. So I'll start by asking the question, how does the physics change if we replace a fluid-filled bottle with a hole with, okay, a fluid-filled bottle with a hose such that, okay, the distance between the fluid surface and the hole would be the same as the distance between the fluid surface and the bottom of the fluid-filled hose. Well, what you would find if you apply Bernoulli's principle is that the physics would be identical. Okay, the physics would not change at all. In other words, the speed of the water that would emanate from the hole at the bottom of the bottle would be exactly the same as the speed of the water that would be coming from the bottom of the hose. Okay, in this sense here, we see this is how a siphon works. You can actually get water to flow, in this case here, or appear to flow uphill, okay, through the hose, so long as the bottom of the hose is at a lower position, okay, than the other end of the hose. So in this little simulation here, we'll see how you can actually get water to actually flow uphill in the action of a siphon.